Okay, as usual, let's start with an example. I want to consider the following two transformations. So consider, let's call this one T, sorry, TA, R2 to R2, given by, we apply it to X1, X2, we get 4X1 plus 3X2 and 6X1 plus 5X2, right? And second transformation, TB, let's say Y1, Y2. Oops. Sorry, I should say that TB also maps from R2 to R2. Two-dimensional space to two-dimensional space. TB, let's apply this to Y1, Y2. Just change of variables. And let's say it's 5/2 Y1 minus 3/2 Y2 minus 3Y1 plus 2Y2. Okay, two totally random transformations. Again, we could write T sub A of X is A times X, where A is the matrix first column 4, 6, second column 3, 5, and T sub B of Y is the matrix B times Y, where B is the matrix whose entries are 5/2. -3 is the first column, -3/2. 2 is the second column. And here's what I want to ask. What is the composition? If we do TA and then TB, or TB and then TA. So compute, let's just say TB composed with TA. Right, so that means we want to do TB, T sub B of T sub A of X, right? You might pause and see if you can get ahead of me and see where I'm going to go with this just by plugging in T sub A first and then trying to plug that in, the result of that, into T sub B. So I would pause, do that. Did you do it? Let's find out. All right, so if I plug in, we're plugging in X1, X2 into T sub A, and we're going to get this formula, right? So that's T sub B applied to 4X1 plus 3X2, 6X1 plus 5X2. And applying T sub B means we're going to put, it's kind of like this is really Y1 and this is Y2, this row. So it's like we're going to plug in this expression 4X1 plus 3X2 in for Y1 right there, right? And 6X1 plus 5X2 in for Y2. And so on. Okay, so again, you should be able to pause and do this and be ahead of me. But if we do that, we get 5/2 times 4X1 plus 3X2 minus 3/2 times 6X1 plus 5X2. And minus 3 times 4X1 plus 3X2 plus 2 times 6X1 plus 5X2. And it's sort of interesting to see what we get. You really should pause now and simplify this and tell me what you get. here, for example, I see 5 halves times 4, 5 times 4 over 2 is 10x1, and then minus 18 over 2, which is 9x1. So there we just get an x1, and then we also have plus 15 halves x2, and then minus 15 halves x2. So that actually goes, x2 goes away. And similarly down here, we get minus 12x1 plus 12x1. That goes away. Then we get minus 9x2 plus 10x2. So this is just x2. And we're back where we started. That should be sort of strange. Basically, right, we did the composition and we got nothing. It did nothing. So that means the way a language I've used before is that T sub B composed with T sub A. Well, first thing I guess I would say is this is true. This applied to X is just X. You just get the same thing you started with back for any X, for any vector X. Or in other words, TB composed with T sub A is the identity transformation on two variables. Right? Okay, that's awesome. Exercise for you. You should do this. Compute, can you guess? Reverse the order. T sub A composed of T sub B. Compute that. Do the same thing. Plug them in the opposite order. If you do that, I claim you get the identity again. So you should get the identity transformation again, the do nothing transformation. So I would try that. Okay, and that this means is that sort of if you apply T sub A and then you apply T sub B, right? T sub B sort of undoes, like T sub A does something to the input numbers, and then T sub B undoes that and gives you back to where you started. Very similarly, T sub A, you know, if you apply T sub B and then you apply T sub A, you get back where you started. So so basically these are what are called inverse transformations. So T sub B is actually turns out to be the inverse transformation. There's only one. Is the inverse transformation of T sub A. It undoes T sub B, I should say, undoes whatever T sub A did. And vice versa. We could also say T sub A is the inverse of T sub B. Okay, so this is the terminology of an inverse transformation. Basically, if the composition gives you the identity. I could write that out very explicitly. It's also in any textbook you look at. Okay. Also on the level of matrices, you could do this on the level of matrices instead, right? So for example, if we do T sub B of T sub A of X, note, or maybe I should say on the level of matrices instead of transformations, T sub B of T sub A of X is by definition B times A times X, right? In terms of matrices, matrix multiplication, which is BA times X. And so let's just compute BA, right? We had B and A were up here. There's the matrix B. There's the matrix A. So let's just do B times A. BA is the matrix. Forgot them already. 5 halves negative. Okay. I should be able to do 5 halves, negative 3 halves, -3, and 2. And A was the matrix, I forgot this too, 4, 3, 6, 5, okay. 4, 3, 6, 5. Multiply these together. Again, pause the video and multiply these together. What do you get? So again, there's 2 ways to go about this. You could just multiply the first matrix times each column. So that would give you the first column of the product, right? Multiplying this times this. And multiplying this times this would give you the second column of the product. Or you can do this sort of, just remember it's like row dot column will give you the top left entry, and row dot first row dot second column will give you the top right entry, and so on, right? So do it, and you should get, in fact, you should be doing the exact same computations if you trace it back to what we did up here. You in fact get like 5/2 times 4 plus -3/2 times 6, right? Especially if you do this row dotted with this column. And so in fact that does equal 1. And then you do this dotted with this to get the top right entry, and it's 5/2 times 3 plus -3/2 times 5, which we also saw gave us a 0, x2, 0, 1. You should check. It's the identity matrix. The 2x2 identity, right? So in general, and again, you should check that A times B is also the identity. So in general, this is what's called the inverse matrix. So B is called the inverse matrix of A. And I can use the instead of A uninverse. It's the inverse because it turns out to be the only one. So the inverse of A. Any matrix where AB equals the identity equals BA is called the inverse. And we denote it, actually, I should have even said this up above when we talked about the inverse transformation. We write here that T sub B is T sub A, and we usually use -1 power for inverse. And similarly down here, we write B equals A inverse. And so that's actually considered the inverse matrix of the matrix A. So, or in other words, I could even write it as the following, that the matrix, so I'll just do A inverse 4, 3, 6, 5. Inverse is 5/2, -3/2, -3, 2. Okay. And so that's, yeah, it sort of comes out naturally from undoing. And the identity comes out naturally because the identity is the matrix for the do nothing transformation, right? So yet another way that the identity matrix is really a multiplicative identity, because if you multiply two inverse numbers like 2 times 1/2, right? 2 times 1/2, you get 1, the multiplicative identity. And here it's just the same thing for matrices. Okay. Okay, so that's the introduction. I'll go into more depth in more videos soon. Okay, bye.